and doctoral degrees in physics in 2004 and materials science and engineering in 2007, all at Arizona State. He was a National Research Council postdoc at NIST in Boulder from 2005 to 2007, after which he became a staff scientist at NIST. He received a Department of Commerce bronze medal in 2013 for his work in magnetodynamic measurements of nanostructures. And as leader of the Spin Dynamics and Microscopy project at NIST, his current research includes the study of spin dynamics and relaxation mechanisms in magnetic thin films and nanostructures, which extends from the nanosecond to the femtosecond regimes, using both microwave and optical techniques. So we're very lucky to have Justin here. Let's thank him.
Great, thank you very much. So, yeah, I'm from NIST, but not the NIST location you visited yesterday, the one in Boulder, Colorado. And there, of course, we focus a lot on measurement science and measurement techniques. So I'm going to shift gears a little bit, and we'll be focusing mostly on a technique called broadband ferromagnetic resonance spectroscopy. And we're going to see how we can apply that to study all sorts of phenomena that's related to the spin orbit. And I've made the analogy to the sort of the Swiss Army knife, right? And here's sort of a picture of a Swiss Army knife. We all know what that is, but it's something that can do a lot of things, right? So it's got, you can open a bottle of wine, you can saw a small branch, it's got a screwdriver, and the like. And by the end of this, I hope to convince you that broadband FMR, or one more specifically based on what we call a vector network analyzer, and I'll explain what that is later, is sort of analogous to that Swiss Army knife. It can do a lot of things in the area of magnetism and understanding and quantifying spin orbit phenomena. So brief outline of my talk. So spin orbit is in the title, and ferromagnetic resonance spectroscopy is in the title. So I'll first give some brief introductions to those two topics. And then we'll get to the heart of the matter and apply this technique to understand anisotropy and orbital moments in materials. Specifically, we're going to be focusing on thin films for this talk. Then we're going to talk about damping and relaxation processes and spin pumping or spin current generation. And then finally, we'll be applying this to understand and quantify spin orbit torques in thin films. So first, to get a sort of basic understanding of what spin orbit coupling is, we can go to sort of the classical picture of the atom, right? Where you've got an electron or a spin that sort of is orbiting around a charged nucleus, as shown here. And then if you, of course, transfer into the frame of reference of that spin, of course, from its perspective, that charged nucleus is orbiting around it, as shown here. And so that looks like a current loop. And of course, when you have a current loop like that, that sets up an effective magnetic field. And it's the interaction of that spin and that magnetic field which gives rise to what we call spin orbit coupling. Now, of course, this is a very flawed example because this is it's not an inertial reference frame. You know, atoms are not really little spheres orbiting around each other. And so to really describe it, of course, it's a relativistic effect. And so you can see this coming out in atomic physics, of course, where you have sort of the Bohr model of the atom, which doesn't include those effects. You've got your discrete energy levels of the hydrogen atom. And then when you go to the Dirac, which is a relativistic function, which includes the spin-orbit interaction, you see that you get lifting of the degeneracy of those levels and the like, which is what we call the fine structure of the atom in atomic physics. Now, for most of us, we usually just treat spin orbit as an addition to the Hamiltonian, given by this equation right here. And here, you're just looking at the overlap between the orbital and spin moments shown here, and the strength of the spin-orbit interaction is given by this parameter here. And you'll see me refer to that many times during the course of my talk, but that just gives the strength of this interaction. And of course, in addition to generating ferromagnetism in materials outright, that addition to the Hamiltonian due to the spin-orbit interaction generates a whole wealth of phenomena. This is even a short list. This is not a complete list, but perhaps some of the more relevant topics relevant to in the area of spintronics, for example. And so it can leads to sort of the development of orbital moments in solids, for example, magnetic anisotropy, which we've already heard about this morning, anomalous Hall effect, topological surface states, and then spin orbit torques, such as Rashba-Edelstein effect, spin Hall effect, which I'll talk about a little bit later in my talk. Also spin lattice coupling, damping, relaxation processes, which I'll also talk about. And then more recently, a hot topic in the field is what we call the Zyloshinsky-Moria interaction. And this is an anti-symmetric exchange interaction, which is getting a lot of press because it helps to help stabilize a lot of these like skyrmion type structures, magnetic topological structures as shown there. And so that was my quick 2-slide introduction to spin orbit and related phenomena. So now let's talk about ferromagnetic resonance spectroscopy. So let's go back to our sort of classical picture of a spin. So we have a spin in blue here, and it's in a magnetic field shown by this green vector here. And in equilibrium, of course, they're going to be collinear, as shown by this. Now we can excite that spin, maybe kick it off of its equilibrium axis by a field pulse or an optical pulse or something, and then we let that go into motion. What you'll notice that it'll start to precess at a given frequency, and eventually will come back to rest, as shown there, and be collinear with that field. Now in a solid, of course, we don't have an isolated spin as shown there. Of course, we have an ensemble of spins shown here. But we can do the same thing, and we get the same sort of behavior, that all these spins will start to precess at a given frequency as shown here. And they can do so in phase, as shown in this example here, which is what we call the ferromagnetic resonance mode. Of course, they don't have to have a zero phase relationship, and you get what you have over here on the right, which is what we call a spin wave or a Magnin sort of excitation. For the sake of this talk that I'll be focusing on, we're going to be focusing on this scenario here, which we call the ferromagnetic resonance mode. Those dynamics are usually described by what we call the Landau-Lifshitz equation. And this is an equation that was derived in 1935. And it wasn't actually derived for what we use it today, which is to describe these dynamics, but was actually originally derived to explain domain wall motion, because FMR wasn't actually discovered till the 50s. But it consists of it's a simple classical torque equation. It consists of 2 components. You of course have the time derivative of magnetization, but you have this torque here, which is what we call the Larmor term. That describes the precessional motion given by this cartoon right here. And then they added on completely phenomenologically a damping term shown here. And so with this term added, of course, you don't get this indefinite precession of the magnetization. It's a lost term. So you get this sort of spiraling in of the magnetization shown there. And the strength of that damping is given here by this parameter alpha, which is the damping parameter. You'll see me refer to that parameter a lot later in my talk. So if you could just keep that tucked away in the back of your heads, that would be great. So of course, we want to be able to measure that. So how do we do that? Well, originally it was done using what we called sort of cavity-based or waveguide-based ferromagnetic resonance techniques. And this is sort of an example. And this sort of goes back to sort of the 60s and 70s kind of. And so this has been done for decades. And it consists of basically a microwave source. So it outputs some microwaves, 10 gigahertz, say, for example. And then they're directed down a waveguide. And these are the waveguides. These are these sort of copper or brass tubes type waveguides. And so they're designed to operate at a single frequency. And so that's sort of the main point here, is that the main limitation of these types of setups is that you are confined to a single frequency. And in this case, your only degrees of freedom, of course, are to sweep magnetic field, because you're an electromagnet, or to rotate your sample. And your sample is usually placed right here in either a shorted waveguide or a cavity or something. And so it was used successfully for decades. And so here's sort of an example where you can measure that resonance condition while you're varying the angle of your sample relative to the magnetic field. And then you can plot those different resonance fields as a function of angle shown here. And that's how you can fit out values of anisotropy and things like that. And this was done successfully for many, many, many decades. Since that time, of course, many different approaches have been used to actually access and measure ferromagnetic resonance using various microwave technologies, optical techniques, device techniques using spin transfer devices, for example. My goal is not to go through and do a review of all those different approaches, and so I just want to skip forward and talk about the technique that we'll be focusing on today. And that's one based on vector network analyzer. And so here is sort of a schematic of how this works. We start off with a VNA, or vector network analyzer. It's a 2-port measurement. So one port acts as our microwave source. So we generate microwaves that are output down a coaxial cable, which is then directed onto a coplanar waveguide. And a coplanar waveguide is basically you have a center conductor that transmits those microwaves, and then you have a ground plane on both sides. And so those microwaves end up generating an RF field, right? A microwave field around that center conductor. And if you take your sample, a thin film sample, and you put it face down on that waveguide, as shown in blue here, then those fields, those RF fields, then can interact with your sample. And that'll change how the transmitted microwaves through this center conductor, which are then measured and picked up on the second port of your VNA, shown here, the receiver port. And of course, you can apply magnetic fields. In this case, it's a perpendicular sort of magnetic field here. And so this is what the data looks like. So because it's a vector network analyzer, that means we are phase sensitive, and that becomes actually quite important. And so we get both the real and imaginary response as we sweep the magnetic field through the resonance. And we simply fit this through the transverse susceptibility. This is just a Lorentzian-like function. It's easily derived from the Landau-Lifshitz equation. I won't really go through it. But the total fitting function, and this is sort of the main important point, is given here. So from this fit, we get 4 pieces of information. One is we get the resonance field, so that's the location of this peak. We get a line width, which is the width of that peak, obviously. We get an amplitude, which, as it says, is the strength of that peak. And then finally, we get a phase. And so that's the relationship between the real and imaginary part. And so this is the very important thing. We get these 4 parameters from this fit. And so from those 4 parameters is really gives us information about different things. So one, from the resonance field, that gives us information about the anisotropy and the orbital moment. From the information we get from the line width, that tells us about the damping, relaxation processes in our sample, the inhomogeneity of our sample, and it also allows us to study what we call spin pumping or spin current generation. And then finally, from the amplitude and phase information, this is where we can now quantify spin orbit torques in our system. So spin Hall effect, Rashba-Edelstein type effects. And so this slide sort of becomes the new outline then for the rest of my talk. So let's go through and step through each one of these individually. So we'll start with the resonance field, where we apply that to understand anisotropy and orbital moments. Now, for this audience, I won't go through in too detail what anisotropy is. Of course, they've probably heard a lot of that all week, but of course, it's the energy, of course, that tends to give a preferred orientation to the magnetization. So here's just an example of a perpendicular anisotropy, right, where the energy is favoring that the magnetization is pointing perpendicular to the thin film surface, as shown here. And of course, that energy difference is what we call the anisotropy energy. Of course, it's important for a lot of things that we've already seen for hard disk drives, MRAM, and things like that, motors, even just primitive technologies such as your compass, right? You always want it to point north. You don't want the magnetization to be moving around. And to understand where anisotropy comes from, of course, we always want to turn to theory. And so a very simple model was developed by Patrick Bruno here that can be used to show some of the origins of where it comes from. And here we have the anisotropy energy, and it's proportional to the difference in the orbital moment along in this case, the perpendicular case, the easy axis, and the hard direction, or the in-plane axis. So the difference in the orbital moments between those two. And the proportionality constant between those, of course, is our friend, the spin-orbit interaction, shown there. Now, the nice thing about FMR is that we can measure both sides of this equation simultaneously. And so how do we do that? Well, first, we have to measure anisotropy. As I've already alluded to before, that can be done using angular dependent measurements. This is the same data I showed already. And then you can fit that out and easily extract those energies. We can do it from a broadband approach as well. And here, for broadband, we measure resonance field versus frequency, and we get a data set that looks like that, and we fit it to what we call the Cattell equation, which is given here. And I won't go through the derivation of this equation, but it's essentially the equation that relates the frequency of the resonance to the resonance field, as shown there. And it can contain energy terms or anisotropy terms of any symmetry that are relevant to your sample. And so there's a good review that actually goes through many of those. But let's just consider a sample that has an in-plane uniaxial anisotropy, as shown there, and the perpendicular anisotropy shown here. And so if we just simply fit this data to this equation, those are just fitting parameters, and we can get this information, and we're sort of done. And there's not much difficulty in doing that. And like I said, it's been done for decades, so I won't spend any more time on this topic. But what's probably lesser known is how we extract orbital moments from FMR measurements. And so another fitting parameter is what we call the spectroscopic G-Factor, as shown here. And the spectroscopic G-Factor is fundamentally related to the ratio of the orbital to spin moments given by this equation. And so if we do magnetometry, we're measuring the total moment of our sample, right? So if you have the total moment, which is the sum of those two, then you could easily separate them out, as shown there. But there's one problem, and that's the fact that G-factors for most materials, metallic sort of ferromagnet materials, is usually just slightly above 2, right? And so it's that slightly above part that we're interested in, right? And so say, for example, if we have a material that has a G-factor of 2.05, and we measure that with a 1% error bar, which is usually pretty good, that actually leads to a 40% uncertainty in measurement of the G-factor, which makes it difficult to actually compare with, for example, theory. And then if you do a literature search, what is the G-factor for permalloy, which is one of the most commonly studied materials in our field? Well, you can see that they're sort of all over the place. And so they vary significantly. And so, again, it makes it difficult to relate this back to theory. So inspired by this, I mean, we at NIST, of course, were interested in precision of measurement and things like that. So we wanted to go have a closer look. And so we started with 20 nanometer permalloy sample. We measured resonance field versus frequency and got this data set right here. And then we went in and we fit, here's our Cattell equation that we fit it to, and we fit out the G-factors. But what we found was that the value we got depended a lot on the range of data that we fit. And let me explain this plot here. So if we fit the data, we have this complete data set, but we only fit the data from 5 to 20 gigahertz, shown here, we get a G-factor of about 2.02. If we extend that fit out to 40 gigahertz, we get a G-factor of 2.09. And again, if we further extend that out to 60 gigahertz, we get a G-factor of 2.1. And we see this time and time again in different samples of different compositions and the like. But what we often always see is that as we extend that fitting range, it asymptotically approaches some value. And so we just start off and make the assumption that it is that asymptotic value that is the G-factor of our system. And by doing so and doing some simple, straightforward asymptotic analysis to determine that asymptote, we can then increase the precision of determining G-factors by better than 0.2%, which makes it easier to, or better to start to compare with theory. Now you're probably asking, well, what can cause all of that? Well, there's many things that can cause it, both intrinsic and extrinsic. One, of course, is it could be simple, just field misalignments. You could just misalign your sample to the field by a fraction of a degree, and it can cause those sort of effects. You might have anisotropy terms that are in your sample but are not in your fitting equation, your Cattell equation. Again, that'll actually cause those effects. But you can also have intrinsic things, such as pinning at interfaces, which is a problem with a lot of thin films. But the point is that we've empirically found that we can achieve accurate values of G-factors, even if we have the wrong Cattell equation that we're fitting to, for example, or have field misalignment issues. So let's apply this then to learn something. So let's take this cobalt iron nickel superlattice type structure here. So this consists of cobalt iron and nickel, which has a strong perpendicular interfacial anisotropy. And so that's why we make a whole bunch of interfaces, so we can increase that anisotropy, total anisotropy. But more importantly is that we can tune that anisotropy by just varying the thickness of the different layers. And of course, it's interfacial in origin, so we expect a nice 1 over thickness dependence of that anisotropy. We fit a line through that, and it behaves as expected. And then we go in and apply that G-factor analysis. So this is the G-factor versus 1 over thickness as well. We measure it in the out-of-plane geometry, and we measure it in the in-plane geometry, as shown there. And you can see by those error bars that they're quite tight at applying that analysis. So now let's just put it together. And so from the G-factor data, we're able to extract the orbital moments in the perpendicular direction and in the in-plane direction, plotted against anisotropy energy, and voila, we get this nice linear behavior, which is exactly predicted by this theory from Bruno, showing the proportionality between those two. The only unknown, of course, is this value of A, which comes from band structure calculations, but it's right in line with what is expected and has been measured in similar sort of materials. Okay, so now let's shift gears and talk about line length and the information we get from that. So why is damping important? A lot of times I have to motivate this point to more general audiences because it seems like an esoteric topic. But of course, damping helps to, is an important parameter that determines the speed at which you can operate a device and, of course, the efficiency at which you can operate a device. And we can see that if we look at a simple MRAM sort of cell here, which is a tunnel junction, right? You have a fixed magnetic layer and you have the free layer that's able to toggle back and forth. And then you have this tunnel barrier right there. And you switch this free layer by pulsing a very large current through this device. And that current, the minimum current needed to actually do that is given by this equation here, and you can see that it is indeed proportional to that damping parameter alpha, at least to first order here. And so we want to be able to control that value in order to engineer these sort of devices. These sort of stacks can also be used in slightly different configuration to do what's called spin torque oscillators, for example. And again, these are used where we can generate microwave emission here, but it has a similar dependence on that damping parameter in terms of the efficiency of operation. And then there's more speculative technologies in the area of magnonics and spin logic. And here, you're taking a spin excitation, such as a spin wave, maybe encoding information in it, and maybe wanting to transmit that down some sort of channel to get it from one place to another. Or you might want to combine many of those spin excitations to do some sort of computation operation. But in either case, of course, if you want to do something with a spin excitation, it needs to be, has to have a long lifetime. It has to be around long enough that you can do something useful with it. And then finally, in the area of spin orbitronics, of course, you know, sort of spin pumping devices where you want to generate pure spin currents and do something useful with those pure spin currents. Again, the efficiency of operation of these sort of devices comes down to the damping parameter. So you want very, very low values of damping in these cases. So let's go back, there we go. Let's go back to the Landau-Lifshitz equation. Now, if you remember, this damping term was just added on phenomenologically, right? It didn't come from any first principles or anything. But if we want to engineer damping in materials, we need to sort of understand where it comes from, right? And so more recently, a lot of theories have come from based on first principles to try and understand where that comes from. And I'm not going to go through and review all those theories, but I just want to say that they all sort of have one thing sort of in common. And I think it's important to go through this to kind of understand the processes that give rise to this magnetic damping. And basically, it comes down to two different types of processes. One is what we call intra-band scattering, which for many of you, if you're in this area of research, is also called breathing Fermi surface damping or conductivity-like damping. So if you see any of these are all synonymous, depending on the author of the paper you're particularly looking at. And so we can understand this, but if we look at the procession of our magnetization. So we go into ferromagnetic resonance, our magnetization is processing, and let's freeze time at time 1, shown here in yellow. And we look at the Fermi surface, shown here. So this is our Fermi surface, and let's say at time 1, it's this vertical ellipse shown here. Now at time 2, at a different time during that procession, the magnetization is going to be a slightly different direction. And so that's going to distort that Fermi surface slightly. And so now our Fermi surface looks something like this in this other ellipse shown here. The problem is that all of these spins that were at or below, in yellow here, that were at or below the Fermi surface at time 1 are now above the Fermi surface at time 2. And so we have to constantly be scattering and repopulating that Fermi surface to maintain equilibrium. And it's that scattering process that gives rise to this damping. We also have what's called inter-band damping, which is also synonymous with what we call bubbling Fermi surface or resistivity-like damping, shown here. And in this case, just as the name implies, we're talking about transitions from one band to the other, shown there. So it can include spin flip type scattering process as well. This depends a lot on the overlap of the different bands in your system. So it depends on the material band structure. It also depends on temperature, for example, or disorder, because the more band broadening you get from disorder or temperature, the more overlap you have. You get increased what we call interband damping. And I'll skip this part here. But ultimately, we want to sort of identify the critical parameters that control damping. It's nice that we understand those models, but we want to relate them to something quantifiable. And so if we go and we look very simply at this equation here, and don't worry, I'm not going through a bunch of equations, so I just want to point out one thing by putting this up here. One is that this comes from this torque correlation model, and one is that it's a summation over all electronic states and bands. So it probably has something to do with the density of states. We have this torque term here, which is proportional to the spin-orbit interaction. So it has something to do with the strength of the spin-orbit. And then it has the spectral overlap, which is a function of our block state lifetimes. So that's something to do with the lifetime. And indeed, a more thorough analysis of these theories does indeed identify three sort of critical parameters. One is the density of states at the Fermi energy, the spin-orbit, strength of the spin-orbit interaction, and the spin scattering times. So if you could just keep those three things tucked away in your memory for the next few minutes, that would be great. So what I just described to you, though, was what we call Magnin electron scattering. Okay, so this is only valid for conductors, right, that have conduction electrons. But there's also a process called Magnin phonon scattering. But this is terribly, terribly inefficient process. Okay, so that's why YIG, for example, insulators such as YIG or ferrites have very, very low values of damping, right? They don't have conduction electrons. They don't have this sort of scattering process. And this is very, very inefficient. However, there's also a whole series of what we call extrinsic damping processes. Spin current generation, for example, those spin pumping sort of process that we talked about, electrodynamic considerations, defect scattering, inhomogeneity in our sample that can all lead to extrinsic sources of damping. And so what started off as this simple phenomenological addition to the Lambda-Lipschitz equation is now turns out to be a very complicated series of phenomena. So how do we measure damping? So let's look at that. This is a talk on FMR, of course. So how do we do this measurement? Well, the Lambda-Lipschitz equation predicts that line width should be proportional to frequency, as shown there. So we should be able to just measure line width, frequency, fit a line through it, and then the slope should give us our damping, as shown here. The problem is that that's not what we often see. And so here's some data taken from a Heusler, a half metallic Heusler compound shown here. It turns out there's actually 4 different mechanisms going on here. And you'd be hard pressed to actually fit a line through this data and believe anything it tells you. And so it turns out we have to take into account a whole list of different mechanisms in these sort of measurements. And I'm not going to go through every single one of them. We just don't have enough time. But I want to step through a few of them because I think it's important to get a sense of the type of processes that occur in these high-frequency measurements or these high-frequency magnetic phenomena, just to give you sort of a taste of that. So, but the main point of emphasis, though, if you're actually wanting to do these type of measurements, is this was where the broadband becomes critical, because you can't separate all of these different processes without it. So let's step through a few of them. So let's first talk about inhomogeneous line width and what we talk about there. So as I mentioned before, Lambda-Lipschitz equation predicts that line width should be proportional to frequency. So we should be able to just get something like this. It goes through the origin as shown there. But what we often see is there's an offset shown there. And so we then just add on this term here, this offset term here called the inhomogeneous line width. And we can see that from a very basic level, that if we have a completely uniform film, we get a nice resonance shown here. But if we introduce a lot of inhomogeneity into our film, of course, we're going to have a whole bunch of local resonances, right? And so in the end, in the case of a high inhomogeneous film, we're measuring basically the envelope of all those local resonances. Now, it's not so simple as a superposition of those local resonances shown there, because we have exchange energy, we have dipole coupling and things like that. But that gives you sort of a little picture to start thinking about it. And we can see this effect in the raw data. So here's an example. We take these cobalt iron nickel multilayers that we already talked about, and we grow them on a tantalum copper buffer layer shown here. Now, we just happen to know that if we sputter copper onto tantalum, that it grows rather rough. And so we can adjust that roughness by just varying the thickness of this copper layer. So we can go from something that looks like this to a surface that looks like that. And so then if we measure line width versus frequency as a function of that copper thickness, we see that that offset increases as we introduce more roughness into the system. But you can see by eye that the slopes are pretty much the same, meaning this value of alpha do not change much in this case. We also have what are called low field loss terms. It's pretty easy to understand. You just simply don't, at low fields and frequencies, you just don't have enough field to fully saturate your samples. You might have domains or maybe curling around edges and things like that, in which case you get this upturn in the line width at these low frequencies as shown here. Now you can fit that to a power law, but to be honest, the best way I feel to deal with it is to simply throw away the data where it becomes nonlinear. So in this case, I would throw anything below 6 gigahertz. Just a word of caution, though, that for some materials, these effects can extend out to very high frequencies. So in this particular case, you would have to throw away data below 25 gigahertz. And we have something also called two-magnon scattering, and this is actually a very important one. So if we look at the spin wave dispersion shown here, so we apply a magnetic field in the plane of our film, shown here, and we look at the spin wave dispersion curves. This is frequency versus wave vector. And of course, our FMR mode is here, because remember, they all process in phase, so k equals 0. But we have all these other spin wave modes that are degenerate with that FMR mode shown there. And so if we can scatter off of defects into these other spin wave modes, as shown there, which is a loss to that FMR mode. Now, if we then apply the magnetic field in the out-of-plane direction, or perpendicular direction here, we see that those degenerate spin wave modes go away. And so we can pretty much eliminate this process by just going to a different geometry. And we can see this effect in the raw data. So here's a simple cobalt iron sample, cobalt iron alloy. And if we measure it in the out-of-plane direction, we get this nice low line width data here. But if we measure it in plane, we get this blue data shown there. And that difference is due to that two-magnon process. It's also defect mitigated, as I mentioned. So of course, if you prove your growth and your seed layers and the like, you can also help mitigate it through that. But you never know for sure if it's there. And now I want to talk about spin pumping and spin memory loss. And this is an important one because we're going to come back to that later when we talk about spin orbit torques. And here, I don't have time to get into the theory of it, but we're talking about a bilayer system. So if you have a ferromagnet, you send it into ferromagnetic resonance. And when you're in that ferromagnetic resonance condition, you get a flow of angular momentum or spin current away from this interface and into the normal metal. Normal metal can be copper, platinum, aluminum, anything like that. But you get this flow of spin current that goes into the normal metal, as shown there. And so that loss of angular momentum is a damping term. And sorry, I forgot to mention, and then we also have what's called spin memory loss. And this is, the origins are sort of unknown at this point, but we're just talking about scattering at that interface. So it's a loss of angular momentum at that interface of currently unknown origins. But in that case, the angular momentum doesn't actually make it into the normal metal. Both of those act as an interfacial damping term. So phenomenologically, we can just treat them as an interfacial damping term. And as with most interfacial effects, we can tease them out by simply doing a thickness series. And indeed, here's an example. We have damping parameter, 1 over thickness. We fit a line through that, and the y-intercept, of course, is our damping with these, both the spin pumping and spin memory loss contributions removed. Now, if you're studying spin pumping, of course, you're more interested in the slope of that line, because that's where all the information about that process is contained. And then we have things such as radiative damping, which is essentially electrodynamic considerations. I won't get into it. There's also effects due to confinement, and you go to nanostructures. You can have additional damping processes come into play. And then there's other things such as slow relaxer, eddy currents, chiral damping, motional narrowing, and a whole bunch of other things, which if you want to know more about it, we can talk more later. But the main point here is that, again, what started off as a phenomenological addition to the Landau-Lifshitz equation, well, it was a scalar and a constant. We didn't even talk about the fact that it's actually a tensor and not a scalar. But it's now not a constant, and it's not, and it's a whole series of phenomena. And so when we put our sample in the FMR spectrometer, this is what we're measuring. It's now a frequency-dependent term. Perhaps we want to relate it to theory. So we're interested in determining the intrinsic damping of our sample. But we have inhomogeneous contributions now we have to take into account. We can do that with broadband measurements. We have two Magnin scattering. Well, we can get rid of that with certain geometry considerations, measurement geometry considerations. We have spin pumping. Well, we need a thickness series. Low field losses. Again, we need broadband measurements. Radiative damping, that's the electrodynamic stuff I skipped, eddy currents, and then a bunch of other stuff that, but we can now have the ability to tease out and separate and quantify all these different sources from these measurements. So I've just inundated you for 5 or 10 minutes on all these minute details and mechanisms going on for line width analysis to try to understand damping. So why did I do that? Well, here's sort of an example about why it's important. So this is one of our recent sort of higher profile results. And what it comes down to is if we take cobalt iron alloys, these are simple BCC, FCC, solid solution alloys, nothing special, no higher levels of ordering. And a few years ago, a few theory papers came out that it said that it exhibits, that they should actually theoretically exhibit exceptionally low values of magnetic damping. And by exceptionally low, at about 5 × 10⁻⁴. And if you don't know, that's about an order of magnitude lower than pretty much any other metal, by almost an order of magnitude. So that's actually significant for a lot of applications. The problem is that the cobalt iron is a very commonly used material, right? It's been studied for decades or maybe even centuries. So why has nobody seen it? And so inspired by these theoretical predictions, we went and made a series of 10 nanometer samples. We varied the cobalt concentration from pure iron to pure cobalt, shown here, and we measured the damping parameter, and we got this red data. And indeed, we see a minimum about where it was predicted in these theories, but it's certainly not this 5 × 10⁻⁴ value. But then we went in and we quantified the spin pumping contributions through a thickness series, for example, and that's shown in gray here. We did the radiative, experimentally quantified the radiative contributions. Those are the electrodynamic considerations I skipped over. And if we then subtract these two from the red data, we see that we get this nice minimum that's actually in agreement with theory. Because when we started off with this, we didn't know if the theory was wrong or the experiment was wrong or both were wrong. But what we see now is that we were actually able to confirm this theoretical prediction. And so that's nice and all, but even more importantly is it gives us insight as to how we can control damping in materials. And so through our collaboration with Ole Eriksson's group at Uppsala University, they did some band structure calculations for this material. And that's shown here. So we have density of states versus energy. Right here's the Fermi energy. So if we take, for example, the iron, just look at the blue data for iron. We see that right above the Fermi energy, there's this minimum in the density of states, as shown here. And as we start to alloy in the cobalt, that minimum shifts lower. And right at 25%, that minimum is centered right at the Fermi energy. And so if we plot the density of states right here at the Fermi energy, given in red here, and overlay that with our damping data, we see that this strongly suggests that it is indeed the density of states that is driving this behavior in the damping. And if you remember that was one of the 3 critical parameters we identified earlier from theory. So that gives us some good insight. And I'll just mention that there were a couple other works that also reproduced this work. We're not the first to actually show that correlation between density of states and damping, as given by these references here. These are usually done in what we call half metals. Prior, it was mostly observed in what we call half metals or Heusler type materials. I'm going to skip this, but one other, just to drive this home with one other example, there's been a long time an inconsistency in the literature as to whether perpendicular anisotropy and damping were related, because they both are proportional to the spin orbit coupling, right? So there was thought that they should also be proportional to each other. And if you did a literature search on this topic, you would see, one would say this is they're linear related, the perpendicular anisotropy and damping. This would say any observed effects were actually due to spin pumping. This one says they're independent. This one says they're independent. This one says they're linear related. And this is the same authors measuring the same material. And they came to opposite conclusions. So what is going on here? Because physics isn't changing from day to day. So inspired by that, we went and looked at those type of material systems. So again, we're going back to these cobalt iron nickel multilayers. We've able to vary the anisotropy, as we've already shown. We measure the damping, and we see that it's pretty much flat for the most part. So there's no dependence that we see with between damping and anisotropy. However, the inhomogeneous broadening seems to be strongly correlated with the anisotropy. And it turns out that a lot of the publications that were seeing that connection were doing single frequency or very narrow range frequency measurements where you were able to separate these two contributions. So again, going in, being able to do broadband measurements and do careful separation of all these contributions allows us to actually separate this out and show that there's no connection between the two. And we already know from the first part that it's not a change in the spin orbit that's responsible for the anisotropy in the system. It's the difference in that orbital moments that we measured in the first part shown there. Okay, so now let's get to the third part of my talk. So for this, I'm going to just give, to actually do this section justice would require an entire complete hour in of itself. So I'm just going to give a very brief introduction to this topic and won't go into the depth that I have in the previous two topics here. And if you want to know more, of course, just come up to me afterwards or send me an email. I'd be happy to share and discuss more. So here we're talking about a concept of spin orbit torques. And this, of course, is a very important topic because of the concept of spin to charge conversion or charge to spin conversion, where essentially you go from a charge current to a transverse pure spin current or vice versa. And the two spin orbit torques we're going to talk about today are what we call spin Hall effect and Rashba-Edelstein effects. And unlike the previous two topics, we're talking about bilayer systems, right? We're not talking about something in a single magnetic film. So we have a ferromagnet and a heavy metal, which has a large spin orbit coupling, such as platinum, which is probably the most commonly one discussed and was discussed in the previous talk as well. So we usually distinguish two different types of spin orbit torques based on the symmetry of the torque. One is what we call a damping-like torque, which has a symmetry here, essentially 3 cross products. And one is what I call a field-like torque, given by this sort of symmetry there. I won't get into it too much, but essentially we usually associate a damping-like torque with the spin Hall effect and the field-like torque with the Rashba-Edelstein effect, although both can have both the Rashba and the spin Hall can have mixed components with the two symmetries. The easiest to understand, of course, is the spin Hall effect. So here we have a ferromagnet in contact with the normal metal. Let's say that's platinum. Of course, if you have a current going down that platinum layer, you'll get a separation of the two spins states, left and right on the top and bottom surface is shown here. And of course, you'll end up getting a spin accumulation at this interface as shown here. And of course, if you have that spin accumulation, that can then exert a torque on this ferromagnet. And of course, it's that torque that we want to exploit to do something useful, such as switch that ferromagnet, or maybe send it into precession in sort of an oscillator type scheme. And indeed, that's one thing that's being looked at. If we go back to our MRAM picture, here's our tunnel junction. Of course, what we usually think of as a two-terminal device, pulse a large current through this device to switch this free layer. Of course, over time, these are really large current densities, and you can damage that tunnel barrier, for example. And so there's some interest to go into what we call three-terminal devices, which is shown here. So instead of switching this free layer by putting a large spin current through this, or sorry, a large charge current through this tunnel barrier, we're now putting like a platinum layer or some high spin orbit material underneath the free layer. And now we're going to drive a large current through this layer, and through the spin orbit torque, we're now going to switch this free layer. And so we're sort of saving that tunnel barrier and just using a small current just to read off the state of this bit. So that's sort of one application as to why this is important. Of course, we want to be able to quantify and measure these spin orbit torques, right? So how do we do that? Well, there's many different approaches as shown on this slide. I'm not going to go through and review the different approaches, but the main point I want to show here is to do that usually requires you to go into the clean room, right? And make a device and do transport measurements of some sort on these devices. And so what I want to show you now in the next few slides is that we don't need to go into a clean room, that we can actually just use VNA FMR and measure the spin orbit torques and quantify them at the film level. So how do we do that? So let's take a closer look at the interaction of our sample and our waveguide. So here's a cross-section of our waveguide. Here's a center conductor. And let's just say we have a permalloy sample bilayer here in contact with a copper layer here. This copper has a low spin orbit, so we don't expect any spin orbit torques in this particular case. So we apply a perpendicular magnetic field. We send in the FMR condition for the permalloy layer, and then we freeze time when the magnetization is sort of in this direction on its precession. And what you see is you'll get this magnetic flux that winds around the center conductor shown there. And we pick that up with the VNA. That's our signal. When we measure FMR, that's the signal that we measure. We'll also get Faraday-generated currents in this copper, but we can sort of ignore them for now. And so the signal we measure here is simply just proportional to the the inductive coupling between the permalloy and the waveguide, given by this parameter right here. That just predicts that the response that we measure is frequency independent, both the phase and the amplitude. And we can see that in the raw data. So we measure it from 7.5 to 35 gigahertz. And we can see the phase and the amplitude are relatively constant in this particular case. Okay, so now let's replace the copper with platinum. So this has a high spin orbit coupling, so we should expect spin orbit torques, or the inverse of that actually in this case. So now again, we go into ferromagnetic resonance with our nickel iron layer, and because of spin pumping, right, we're going to generate a pure spin current going into the platinum layer shown here. Then that pure spin current through the spin orbit torques will be converted to a charge current. And so in the case of the Rashba-Edelstein, it turns out because of the symmetry, that charge current at this point in time, this snapshot in time, will be in this direction. The charge current to the spin Hall effect, it will be into the plane of the film as shown right there. And of course, if you have a charge current going this way, that's going to create an Ørsted field that will then couple to this waveguide as shown there. But the main point is of course we have 4 parts of our signal. We have the inductive coupling from our permalloy layer. We saw that before. We have the Faraday currents, but we can sort of ignore those for now. But now we have 2 more additions. We have the signal from the spin Hall, the damping-like torques, and that from the Rashba-Edelstein effect here. The main point here is that these are now frequency-dependent terms. And so the total signal we measure now has this term which we saw before, which is frequency independent from the permalloy, but now we have a frequency dependent inductive coupling term shown there. And so what turns out is that predicts both a change in amplitude and phase of our response. And indeed, if we measure 7.5 to 35 gigahertz, as shown here, the same range we saw in the earlier slide, we see both a shift in both the amplitude and phase. And it turns out through a lot of analysis and a lot of equations in this reference here, I'm not going to go through it, but we can actually quantify and separate out those torques from this type of data. So let's apply this to try to learn something. So we'll show one sort of example why this is very useful. So there's also been an inconsistency in the literature about what we call the spin diffusion length of platinum, right? And so for folks that measure it using damping measurements, spin pumping type measurements, shown here, usually end up getting a very, very small value of that spin diffusion length, on order of a nanometer, maybe even less than a nanometer. And you can see that here. So you can essentially think of this as the damping parameter here, and this is the thickness of the platinum layer on top. And so you can see that the damping jumps up very quickly and levels off around the sort of nanometer regime. You can just kind of see that by eye a little bit. But if you take the same bilayers and you go into the clean room, you make these devices, and then you measure the spin Hall effect using transport measurements, you see here that it's a much more gradual process. And so if you were to extract the spin diffusion length of platinum in this case, you can see by eye it's probably closer to 10 nanometers in this particular case. And so what's going on? Because they should give the same result, they're both a result of that spin pumping current, the spin current going into the platinum layer. So we went to have a closer look at this, and so we made a series of samples. So we have a ferromagnet, I think it was 2 nanometers per molloy, and we varied the thickness of the platinum on top, as shown here. And then using the method that I described in 2 slides ago, we measured the spin orbit torques. So this is actually spin orbit conductivity, that's the spin orbit torque, versus the platinum thickness. And what we see in black here is the spin Hall effect. And we can see just by eye that that's consistent with the device data, right? It gives a spin diffusion length somewhere between 5 and 10 nanometers, consistent with the device results. But since it's an FMR measurement, we're also simultaneously getting the damping and the spin pumping data. Same samples, same measurement. And so we can plot that here as well. And so we have damping versus thickness of platinum. And we can see that's consistent with the previous spin pumping results. We have a very short spin diffusion length, right? It just sort of falls off a cliff at very low thicknesses. So it actually turns out from this result that what's going on here is because we're able to now self-consistently fit both sets of data simultaneously to the same theory, that it turns out that the problem is this what we call the spin memory loss, which I alluded to earlier. So remember that for the spin pumping, of course, we get this spin current that goes into the platinum. That's what generates the spin orbit torques. And then we get this loss term at just the scattering at the interface, which we call spin memory loss. That's angular momentum that's just lost. It's gone forever. So the problem is that in spin pumping measurements, we cannot distinguish between the spin pumping and spin memory loss. So we're measuring the summation of those. And it turns out the spin memory loss is actually dominating that process. In the spin orbit torque measurements here, we're only measuring the spin pumping contribution. It's not sensitive to this at all. And so what it turns out is now we're actually able to separate these two. And that has 2 consequences. One is now because we can separate them, we can start engineering that interface better. So we can more efficiently get all that angular momentum into the platinum to do something useful or across that interface. And the second thing is because a lot of that angular momentum is being lost to spin memory loss, the efficiency of the spin orbit torques actually might be greater than what we think. So we might be getting the spin Hall angle of platinum, for example, might be larger than what it is we think. So I'll just skip this, the disadvantage slide. Before I summarize, I just wanted to quickly acknowledge the hard work of many people that went into the results I showed, particularly at NIST. I want to acknowledge Hans Nembach and Tom Silva. As I also mentioned, from the damping work, we got a lot of support and help from Ole Eriksson's group at Uppsala University for theoretical support. And then also in the damping, we had some additional contributions from Christian Bach and Bert Koopman's group as well. So here is my summary slide. So I showed you that the spin orbit coupling leads to a whole wealth of phenomena, many of which are important to the area of spintronics and spin orbitronics. But I also hope I convinced you that recent advances in VNA FMR technology gives us better access and new access to many of these phenomena. And in particular, I've shown that we can better precisely measure orbital moments in materials that we can relate to theory of anisotropy and the like. We're able to quantify and determine intrinsic damping and extrinsic sources of damping. Again, it allows us to compare to theory, but more importantly, to be able to engineer relaxation processes in materials. And then finally, a new sort of method by which we can extract spin orbit torques and quantify spin orbit torques and samples without actually going into the clean room at the film level. So with that, I thank you very much for your attention. Oh, sure.
Thank you for the interesting talk. Actually, I have a question about the FMR spectroscopy. In the general cases, when we have from 3 to 4 parameters and we fit them, what can be the argument that on the uniqueness of the solution? That when we change this parameter in another way, we find the same fitting. What can be?
What type of parameters are you referring to? You're talking about the anisotropy or?
Assuming the case we have the resonance frequency and we have first order anisotropy, second order damping, etc.
Okay, so we're going back. Let me just go back to that slide. Let's see. So you're talking about when you're fitting your Cattell equation, essentially. That's not the slide. So you're talking about in this particular case. Okay, so I didn't want to get into it too much, but essentially I think what your question is in this particular case, let me back up. Sorry, it's going the wrong directions. Sorry about that. Of course, we have a uniaxial in-plane anisotropy. Mm-hmm. What I didn't mention actually is we do have to orient the sample along a specific axis for this measurement. We can't just have it randomly oriented in this particular case. And of course, we have a perpendicular anisotropy right here. And I don't think I have a back slide. We can actually separate out the first and second order, for example, perpendicular anisotropy by measuring the sample in plane and out of plane. Because this M effective term here for the out of plane direction contains both the first and second order anisotropy terms. And for the in plane case, as shown here, only contains the first order. And so if you measure them both, the difference is the second order. And I'm not explaining this very well because unfortunately I don't have a good slide to show you. If you have a whole bunch of anisotropy terms, then of course you can't do it along a single axis. You have to do these measurements along multiple axes to actually separate all the different terms. And I don't know if that answers your question very well or not, but.
Thank you. I have another broad question.
Yeah, sure.
It's about the damping constant. We always have it like 0.01 or 0.03 or 2. My question is that, is there something, other digits that can make it more precise, or it's intrinsic like 0.01, 0.02? Is there some other numbers after those 2 and 1?
Well, I mean, it's dependent on the material, right? I think often, so there's 2 things there. One is, of course, it is dependent on the material. So for example, let me just go back to this. My background, okay. So let's just take cobalt iron, for example, right? So we're going from pure iron to pure cobalt. And we can see that the damping parameter changes as a function of composition. So again, that's material dependent. The slide I skipped over, maybe I shouldn't have, here, is of course, if you're operating a device, it's nice that the intrinsic damping is whatever it is, but ultimately, it's the total damping that determines how your device operates. And so, for example, we know that this cobalt, and this is an example where we have this low damping cobalt iron. So we know the intrinsic damping of this cobalt iron is 5 × 10⁻⁴, plus or minus whatever. But the problem is in a device, you're gonna have a complicated structure. And so take, for example, here where we use a copper tantalum seed layer, for example. It's nice that the intrinsic is so low, but ultimately if you have a 2 nanometer film, the total damping is actually is 0.005, an order of magnitude larger. And that's really what matters. But if we know what the intrinsic damping is, we can also start to engineer the spin pumping contributions. And for example, by getting rid of tantalum in this particular case and replacing it with titanium and aluminum, we can get for example, this 2 nanometer film with a total damping much lower, shown there. And so it's all about, I don't know if I'm doing a good job of answering your question or not, but certainly the intrinsic damping is material dependent. The total damping is, of course, even depending on spin pumping contributions, such as what it's in contact with. As we can see that we can vary that very dramatically in this particular case by changing the other layers in the stack. So there is no one damping parameter that can be used. So that was a very long-winded way of answering your question, maybe, but yeah.
Thank you.
Hey, Justin, very nice talk. Maybe I misunderstood, but I thought you said that the inhomogeneous broadening and the anisotropy were proportional in one of your slides.
No, not proportional.
Well, related.
If I said that, I did that in error.
I misunderstood.
What I meant to say is that the inhomogeneous broadening increases a lot as the perpendicular anisotropy is increasing. So here we have anisotropy. So here's when we have perpendicular anisotropy is actually negative values here. And so you can see that it's very, very low. And then as you start to go to a net perpendicular anisotropy, it starts to increase, as shown there. And we see that consistently with a lot of materials.
So you're just saying as you go to larger perpendicular anisotropies, you're getting more inhomogeneous broadening.
Correct. Yeah.
In that system.
I can't generalize that to all materials, just the ones that we've observed. And I guess you could kind of hand wave it that that maybe the fluctuations in the anisotropy due to the interface. I mean, that as that interfacial anisotropy or some other anisotropy gets increased, then fluctuations in the order parameter or the interface conditions can give rise to large fluctuations of the local anisotropy. I'm just hand waving here.
Yeah.
We don't know. The short of it is we don't know exactly, but we consistently see this.
Okay. I think there are counterexamples as well. So
there are probably. This is not a generalized thing, but the examples I showed here were with these multilayers, these cobalt nickel multilayers, and so that's why I was making this. No,
one of the problems we've had over the years is trying to measure peer order anisotropy, and this is a system that we've always suspected had peer order anisotropy. Because the Z is so similar, it's virtually impossible to measure it directly. But I was wondering if this is a technique that you can kind of pin that down.
I don't know if I have a good answer for you on that.
I mean, you'd have to look at maybe a cobalt iron 50-50,
right?
And then look at quenched versus annealed. But it's something that has been a problem for us for many, many years.
Yeah. I don't. I would say maybe. Yeah. I'm not an expert on that particular.
Maybe.
I'm not an expert in that, but maybe we could talk more, and you could fill me in.
And before I let you go, the G-factor measurements you are making, have you been able to compare those to single crystals to see how close you are, like from past years?
What do you mean by compare?
Well, you were saying that it was very dependent over the range of frequencies,
yes.
and it was converging to 2.11, right. I think it was.
For permalloy, yeah.
For permalloy, I can't imagine that in some of the older literature that single crystals in spheres
Right.
are measured. And I was wondering how your data.
Well, with the thing to take into account, though, too, is the G-factor along different crystalline axes was probably different as well. I mean, in permalloy, of course, it's very low anisotropy, and you may not expect a big difference. The other issue there is that most of those measurements were done with cavities, and which is typically 9 point whatever gigahertz sort of frequencies. I don't have a good answer for that. We did a literature search on every reported value we could find, and maybe we missed one on some of these spheres or whatever. I don't remember coming across one, but yeah.
Actually, first of all, brilliant talk. And so I have a question. It has been shown that in systems, cobalt iron boron platinum, or actually metallic and platinum systems, that there is a proximity effect and that this increases the damping. So this could also be attributed to this band structure shift, right?
What do you mean by band structure shift?
I mean, you told that the damping depends on
the density of states?
Yeah, the density of states, yeah.
So in that particular case, we have, you can get rid of the proximity effects by actually just putting a very thin layer of copper, right? We don't see a huge difference in that particular case, because in that particular case, usually your damping is dominated by spin pumping. And so how it affects the intrinsic damping, if you have a thin layer of permalloy and you have platinum, most of the damping is from here. I actually have it, that slide. And so from that perspective, we don't see a huge difference. Where is it here? See my wife in Milan again, so. So here, using this sort of self-consistent fit, so we separate out the different contributions of damping. So the red here, that's the intrinsic damping of the sample, of permalloy. We of course have some spin pumping contributions into the seed layer. We had to use a tantalum layer to get some good growth. And then we have all of this is due to the platinum, right? Whether it's spin memory loss or spin pumping. And so the intrinsic damping is just a very small part of this whole picture. And so in the end, you're correct, maybe in the sense that it might modify the band structure or the density of states at the interfacial region. But it's hard to see because that would be a small fluctuation down here on top of a very large series of other contributions. Is that?
Actually, I'd be happy if we could discuss this later, maybe, if you have time.
Sure.
Okay, thank you.
I don't know. It's like,
how that works. I have a small question. Thank you for your nice talk. I'm really interested in the SOT measurement by using FMR method without fabrication. This method should be very efficient compared to devices measurement. But I little worried about the precision. Could you please talk more about the precision between several methods like FMR, STFMR, and harmonic measurements?
I'm sorry, can you?
Yeah.
Precision.
Yeah, precision.
Oh, okay. Yeah. So one of the things, of course, you're wanting is probably a comparative study, right? Which is in process.
Yeah.
So we are indeed. So where was it? So all of these devices those are pictures of our devices. So we are actually going through right now and doing a comparative study. In terms of precision, I mean, you can see the error bars on this. That's, of course, if the analysis is correct, of course, right? But that's true for all of these approaches. And so you can see the error bars that we get applying this method. Fitting it to the equations that we use. Now, if equations are wrong, of course, that's a different topic. But I don't know. That's the best I can answer your question concerning precision.
Okay, thank you very much.
So people talk about the spin orbital torque generated by ferromagnetic layers. So I'm just wondering, through your measurement, can you, especially in the nickel and platinum case, can you distinguish the different contributions from the nickel ion and from the platinum?
Yes, so I think it's up here. So actually, it was just published today, but we did that. Actually, just in nickel, as nickel copper, where we go from ferromagnetic nickel to paramagnetic nickel. And we actually do measure that in nickel directly.
But that case, you only have a ferromagnet, but in the nickel ion and the platinum, you may have two sources, right? From platinum,
yeah,
also from the nickel ion. Can you distinguish that from the measurement?
Yes, yes, yeah.
Can you go to the slide number 37 in your presentation?
This.
Yeah, so the line width versus frequency graph, because G is so sensitive to the range of frequency. And if you see the higher frequency range, so there is a large deviation between the line width as a function of frequency.
So sorry, I understand your question, sorry?
So in this graph, at higher frequency, for example, from 40 gigahertz to 50 gigahertz, the deviation of line width is quite changing. Like
you're talking about like the scatter?
Yeah.
Yeah, I mean, this is actually rather old data. So it actually comes out that our waveguide just isn't very flat in its response there. So you get these regions where you get much higher signal to noise, and you might get these little wiggles out. And then it just means it's a function of our microwave circuit, which we've improved on since this time, but you can get little resonances in your waveguide and things like that that cause that. And of course, your signal to noise drops as you go to higher and higher frequency because the losses in your microwave circuit get larger and larger the higher frequency you go. I don't know if that was.
Yeah, I'm thinking in terms of G value, because if you.
In terms of G value?
Yeah.
Okay, so this is line width that we're plotting here, which usually has a lot more error and scatter in it than the actual resonance field. And so if you just compare that, for example, that's just a typical line width sort of data, and you compare that to the resonance fields, right? Where was it? Yeah. Right, you can see how we're measuring all the way out to 60 gigahertz, and we don't see any wiggles, so to speak, in this particular case. It's a different sample, I understand, but the point is this is not as susceptible to, because this is spectroscopic, right? This is a position of a peak. Measuring the width or the amplitude is not as it's not a spectroscopy. You're not measuring just a frequency, right? You're measuring some width or amplitude or something. That's where errors start to come in, and how your microwaves, differences in your microwave circuit come into play more significantly. Yeah.
All right. Thank you, everyone, for your attention.
So, I don't have anywhere to be, but it's up there.
Thank you. I have a question about you neglect the damping factor of eddy current loss. You said it's usually you can neglect it when the thin film is thinner than 20 nanometer. I'm wondering what's the frequency or skin depth to reference.
So, yeah, that was an overly generalized statement that I probably should not have made. That was specific to a particular sample. So It's dependent on the conductivity of your sample, and it's dependent on the magnetization, saturation magnetization of your sample, right? So if we take this cobalt iron layer, for example, we can see the different contributions. So this is the additional damping on top of the intrinsic versus thickness. And you can see the spin pumping, of course, gets larger as you get really thin. Your radiative damping, which I skipped over, is sort of linear in thickness. And then your eddy currents are quadratic in thickness, as shown here. And all I was saying that, you know, this curve, I mean, this is the equation, right? So it depends on resistivity, thickness, magnetization. That actually determines that cutoff point. For this sample, I would say maybe below 20 nanometers, you don't have to worry about it. You know, obviously at 100 nanometers, it's a pretty significant contribution. So sorry. Can you?
In one paper, in some paper, this exponent has a C divided by 16 factor instead of 8. So what?
Yeah, I'm not going to remember that right now. He's saying that in some papers this is a 16 versus 8. I don't know if it's a, maybe there was a factor of 2 that just got absorbed somewhere. I don't know, but yeah.
Yeah.
Oh. Oh, in this, right here. Okay. In my own figure. Can I say the same response? Yeah, I'm not sure which one is correct, but I'll just point you to those references. I don't remember.
Factor 2 among friends as well.
Yeah, exactly.
Let's thank Justin again. Okay, some stuff with regard to